Hi, my name is Dalton Hensley, and today we're going to be discussing my midterm Capstone report, specifically the Moorhead Azalea Capstone compiler. Again, my name is Dalton Hensley, and my mentor helping me with this project is Dr. Elgazar. So to begin, we have 7 core topics to discuss that will sort of guide us through this presentation. The first is a personal introduction of who I am, what my interests are, and where I sort of fit within this project. The second is the project itself more generally and what my requirements will be. This is followed up with some related work and the current trends within this space, as well as a discussion over the potential risks, as well as their inevitable difficulties that probably will arise. But of course, it's important we discuss the current progress and as well as any future work beyond just what this presentation shows. So I'm a 4th-year student at Moorhead State University. I come from a very small county, I guess, Belfry, Kentucky. And, well, actually, Belfry is the town, but the county is Pike County. And it's about as far east in Kentucky as you can get, but it's where I call home. My central interests in computer science currently are emulators, compilers, and operating systems. It is fascinating to me that while these subjects are very different from one another, oftentimes when I'm writing an emulator or the current compiler that I'm working on now, I draw a lot of inspiration from these projects, and I think that in itself is pretty cool. And then the last thing I want to say about me is that I'm a twin, which is pretty neat. So this is an example of one of my past projects called the Chip 8. The Chip 8 was a virtual machine that was developed in the late 70s, and my goal of this project was to emulate it. And actually, the way we did this is by implementing an interpreter for this virtual machine. And it was actually pretty successful because it allowed us to play some of the games that ran on Chip 8, such as Pong. Another project which I think has been enormously helpful developing the Capstone compiler is my other language, which is interpreted. So this language is named Spiral, and it differs in that, again, it's interpreted, and the Moorhead Azalea compiler is compiled ahead of time. So as I've alluded to already, the central idea here is to build a compiler and its corresponding integrated development environment. So the central design is ahead of time, static, and all work should be done at compile time rather than being deferred at the program's runtime. In order to maximize the user's enjoyment and efficiency with writing these programs, we've also concurrently been building the integrated development environment, which is written in Python. But I believe that the IDE will greatly complement the compiler. This project overall, though, has 3 core tenets or requirements. The first is the grammar that defines Azalea, and we really can't move on to anything else until we sort of figure out how the grammar sort of defines the rules of the language. And so once these rules are established, then we can go ahead and work on the compiler's implementation. And this implementation has been implemented using a pipeline. And then the last thing we should discuss is the integrated development environment. So the formal grammar is largely a specification of how the language, or how any set of valid strings make a map to the Azalea language. So it is not enough to just have a universal language. Actually, we want a context-free language that very specifically maps our production rules to the terminals and non-terminals that make up the source files. So beyond the grammar, though, we actually need a compiler that implements it. And one architecture design that we've gone with is pipelines. And pipelines are a known architectural design that makes excellent use of pipes and filters. So these pipes are what connects these things called filters. And within these filters, you might have some mathematical transformations that take the output of one filter into or as input to the next filter. And we've sort of consecrated this design on 5 filters. These filters are preprocessing, scanning, parsing, semantic analysis, and code generation. And the first filter that makes up this pipeline is preprocessing. And there's 2 core tasks that make up this filter. The first is comment stripping, so any C-like comments are eliminated and stripped out before any further processing. The next thing that we do is we verify character codes. So if there's some non-ASCII character, we want to both detect it and report it to the user. So here's a sample example where preprocessing should fail, and it's actually a good thing that it fails and alerts the user. So in line 4, we say let ? be 2. Now, the mistake here is that the question mark is not supported as a character code for this language, and then we detect and report this to the user. Following preprocessing, we do scanning, and scanning is a lot more complicated than preprocessing actually, because in the scanning phase, what we want to do is determine the atoms or tokens that more or less make up the program. So the punctuation, such as semicolons, or the actual words, such as the like any keywords, for example, such as or main, need to be detected. Here's an example of running the compiler and printing out the token stream. The first token that we actually see here is main. We have a lot of additional information, such as the location of this keyword and whether or not it's reserved. Following scanning is the parsing phase, and one common trend throughout all these filters is that they're increasingly more complicated than the previous one. So parsing is more complicated than scanning, at least in my implementation. But actually, this is where we connect the formal grammar that we've already defined, and we represent it as a data structure. This data structure goes by many different names, but the one that I'm currently using is called an abstract syntax tree. Here's an example of such a tree, where at the very top we have the start node, and at the very bottom, or actually as we sort of comb our way through this tree, we get different production rules, we see the non-terminals and terminals, but the whole actually represents the source code altogether. Here's an example of parsing that fails. So we say let ! be 2. Now, exclamation mark is actually a valid character, so preprocessing will actually pass. Scanning will also pass because all of these are valid tokens. Parsing, though, will fail because we don't expect a exclamation mark here, we expect an identifier. And here's the associated error. And this is a syntax error, to be clear. So some related work to, I guess, programming language theory that I've been kind of interested in as far as these past few years is Jonathan Blow's Jai language. And Jai has, to my understanding, 2 pretty neat features. Jai uses arbitrary compile time evaluation, so basically anything can be done at compile time. And then the second feature is transforming an array of struct type representation to a struct of arrays. And this is good for modern processors, which greatly exploit like spatial locality, for example. And so those are the neat features of Jai. The next is Veils, the Veil language, and Veil actually is trying to work out a more efficient way to create a memory-safe language with very little overhead. And the way that it's doing this is by using something called generational references. And a proper discussion over what generational references are is beyond the scope of this presentation, but that's currently the focus of Veil. And lastly is Coca. Coca is a language that is trying to employ effect systems to track side effects using types. And so I think that's pretty interesting too. But going back to our project, there are some potential difficulties and risks. The first is that I've never implemented a type system on this scale before. I've implemented a basic one in Spiral, but not in Azalea currently. And so this is actually pretty risky for me. The second risk is using LLVM and its ecosystem. I've never used LLVM, so at this point it's a big mystery. And then the final risk is that LLVM-IR, the intermediate representation, might just be too cumbersome to use in practice. I don't think this will be a big issue, but considering I've never used LLVM, it's always a possibility. The last thing to mention is Azalea's integrated development environment. So by default, it comes bundled with Azalea. So as an alternative to the command line interface, a user doesn't have to type all these commands, and maybe a developer of the compiler would actually prefer the commands, but end users probably want a integrated development environment. It's built currently in Python, so speed is not a priority, but having quick implementation of this IDE is greatly appreciated. And so the features include opening and saving project files, as well as the ability to build and run Azalea programs. Here's a little snapshot of what you can expect from this IDE. The top panel is where you kind of write out your code and run it, and at the bottom is a display panel that shows you the output. The current progress is as following. The IDE is in a very good state and is actually functional. The preprocessor, scanner, and parser are also functional, meaning that they work as expected, and ignoring any potential bugs or things we want to go back to, they are largely finished. The semantic analyzer and code generator are currently in progress. So the second half of this semester, as well as going into next semester, will focus on these two components. And like I said previously, future work is largely or predominantly focusing on the semantic analyzer and the code generator. During the semantic analyzer, we want to do type checking, we want to do scope resolution, use after free checks, stuff like this. And once a lot of this undefined behavior is sourced out and located, we want to try to do some code generation with LLVM-IR. And then I guess following this, we want to convert the LLVM-IR into an executable program, which will be handled by the LLVM platform. And I guess to summarize what we've said so far, here's a small diagram going over the project as it currently is and as I expect it to be. So on the bottom left, we have a programmer who writes the Azalea source files, and then this gets fed into the Moorhead Azalea compiler. And then the first thing we do is pre-process this data. We then scan for tokens. This is then converted into the AST and the symbol table. And then using the symbol table and AST, we do some semantic analysis checks on it. And then once a lot of the trivial mistakes are detected and eliminated, we'll then do code generation. And then we have, hopefully, a properly working executable file which can be stored to the user's computer. Here are my references. And I guess to conclude, I want to thank you for watching this presentation, and I hope to conclude this project successfully and And another thing is I want to thank Dr. Okazar for helping me out with this project. Thank you.